In this video, we continue with chapter 5.2 examples and concepts. And so we are going to introduce ourselves to theorem 5.7, which is three properties of inner products. So if U, V, and W are vectors in an inner product space V over the real numbers, and C is a scalar, and so that means C is also a real number. So that's what our little arrow up here is saying, over the real number. So C is a real number. Then all three of these properties hold. So by symmetry, zero inner product with V is the same as V inner product with zero, which is going to be zero. And notice in the inner products, those are the zero vectors. But our total is going to be a value, and that value that it totals is zero, just zero the number. That's why it's not in bold. And then U plus V inner producted with W is going to be U inner product with W plus V inner product with W. And U inner product with a scalar C times V is going to equal the scalar C multiplied by the inner product U and V. Okay, and so notice this is only over the real numbers. So these properties were not true for general definition of vector spaces and inner product spaces that we saw back in the definition. So these are extra properties that hold if you're over the real numbers because of the commutativity and associativity of the real numbers that we're able to invoke here. Okay. The proof of part one is by the symmetry property. So this holds for real numbers because we know right here you can factor that zero out because it's a scalar and the real numbers. And so you get a zero here. And then by symmetry, we know V inner product with zero is the same as zero inner product with V. Then part two, we're using symmetry here and axiom 2 of the definition of vector spaces. And then we can rearrange by the symmetry. And we get that this is U plus V inner product with W is the same as U inner product W plus V inner product W. And then part three, because we're in the real numbers, we can pull that scalar out and then we can use the symmetry to rearrange and we get UV. So just know if you're working with complex numbers, it may not hold. So you'd have to verify if these properties work in other systems besides the real numbers. For our class, we're almost entirely going to be working with real numbers. We'll do a little bit at the end of the semester with complex numbers. But no, this set of properties are just over the real numbers. Okay, so together with the inner product axioms, theorem 5.7 is saying that the inner product is linear in each of its arguments, and we're going to study linear operators much more when we get to chapter 6. So linearity is essentially the same as the distributivity, where we can distribute values through, like in the distributive property. So here we've got the dot product and the general inner product. And so you can see the linearity there when you do the dot product, that you get the values here and that we've got sums. We don't have any higher powers, like no second order, second exponents, third exponents, anything like that in here. Okay, so we're going to let U and V be vectors in the inner product space. And so we're going to define the norm is going to be the square root of the inner product of a vector with itself. The distance between two vectors is the norm of U minus V. So this is very similar to what we saw with dot products. And then the angle between two non-zero vectors U and V is given by theta equals the arc cosine of the inner product of UV divided by the norm of u times the norm of v for theta angles between 0 and pi. So again, these properties here are all the analogous properties that we saw for dot products, and the proofs are actually the same as what we did for dot products. You would just generalize it to inner product spaces. So we did a special case of inner product spaces when we did these calculations and definitions and proofs for the dot product. And then two vectors u and v in Rn are orthogonal, which we think of as perpendicular. They meet at a right angle or 90 degrees or pi over 2 when their inner product is 0. So when we check for orthogonality of vectors in Rn, we're going to calculate the inner product and see if it's 0 or not. And the important note here is notice that the 0 vector is orthogonal to every other vector. Okay, so if the norm of a vector u is 1, then u is known as a unit vector. If v is any non-zero vector, and it has to be non-zero because we don't want a 0 in the denominator, then the unit vector in the direction of v is going to be v divided by the norm of v. And then notice the definition of the angle assumes that our values here are between -1 and 1 for this calculation here of the inner product of uv over the norm of u, norm of v, because that's the domain for arc-cos. And so this is guaranteed by Cauchy-Schwarz inequality. So here are some properties of the length. The length is going to be greater than or equal to 0, and the length is 0 if and only if the unit vector is 0. And then scalar multiplied by the unit vector in the norm is going to be the same as the absolute value of that scalar multiplied by the norm of the vector u. And so these all follow from those axioms that we had in the definition of the inner product and the definition of the norm. And we showed these for the dot product case in chapter 5.1. And then here are properties of distance. The distance between u and v is going to always be non-negative when we do the norm calculation. It's greater than or equal to 0. And the distance between u and v is 0 if and only if u and v are the same vector. And then because it's non-negative, because when we work through that formula, we've got the inner product and then it gets square rooted. So we know we're going to have all positive values there. It doesn't matter the order that you calculate your distance in, you're going to get the same result, whether you do distance from u to v or distance from v to u. And that's because of this non-negativity in the calculation because of your inner product properties. And so these properties of distance all follow from the axioms and the definition of inner product, and then how we're defining distance. And again, you can see these are just extensions of what we did with the dot product back in chapter 5.1. So now we're going to go back to our example with A and B being two matrices in M 2x2. And we're going to use this same definition of inner product that we showed was in fact an inner product in the earlier example. And then we're going to let I be the identity 2x2 matrix. R is going to be the matrix 0, -1, 1, 0. And L is going to be the matrix 5/4, 3/4, 3/4, and 5/4. And so we're going to do some calculations here. So let's start by finding the norm of I. So that's going to be the square root of the inner product of I with itself. So that's just the square root of these calculations, 1 times 1 plus 0 times 0 plus 0 times 0 plus 1 times 1. So we get the square root of 2. And then let's do the inner product calculation of and the angle between matrices R and L. Are they orthogonal? So I just pasted here again, matrices R and L, so we wouldn't forget what we were working with. So it's just, remember, component-wise multiplication for this inner product definition. So each component gets multiplied by the component in the similar place in the other matrix. So that's how I got my multiplications here. I got 0 times 5/4 minus 1 times 3/4 plus 1 times 3/4 plus 0 times 5/4. So I get cancellation here with my minus 1 times 3/4 and my plus 1 times 3/4. So I get an inner product of 0. Remember, when the inner product is 0, that's meaning that the angles pi over 2 are 90 degrees, and we have orthogonal vectors here, where vectors is in the general sense, where 2 by 2 matrices are considered vectors in the vector space M 2 by 2. So these are orthogonal, and we showed that by showing the inner product is 0. So now let's find the inner product of the angle between I and L. And are those orthogonal? So I pasted vectors or 2 by 2 matrices, I and L here. And so when we do the calculation here, we're just again doing that component-wise multiplication. So we get 1 times 5/4 plus 0 times 3/4 plus 0 times 3/4 plus 1 times 5/4. So no cancellation here. So this works out to be 2 times 5/4 or 5 seconds or 2.5. And so they're definitely not going to be orthogonal. And then you want to now to find the angle, figure out the norm of each of these. So I inner product with itself gives us a 2. We saw that earlier. And then L inner product with itself gives us 5/4 squared plus 3/4 squared plus another 3/4 squared plus another 5/4 squared. So that's 17/4. So when you root that to find the norm, that's root 17 over 4, or simplifies to root 17 over 2. So that's where this down here comes from. And so just plugging in our values down here, we've got the inner product up top divided by the norm of I and the norm of L. And so we're going to take the arc cos of this to get our angle. So you can verify on a calculator. Let's see, you could rationalize the root and call this 5 over root 34, because your 2's here are going to cancel. So we didn't actually rationalize the root in the bottom. We just simplified and canceled. So the arc cos of 5 over root 34 is 0.54 radians, or about 31 degrees. So it's definitely not orthogonal. And we knew that back up here when we saw that the inner product was non-zero. Okay, let's look at another example. We're going to let P and Q be 2 polynomials in P. So that's just P1. So those are all the polynomials of just first degree. So those are just the linear polynomials, or the constants, which are also technically linear. And then we're going to define the inner product of P and Q as the integral of -1 to 1 of P times Q. So let's find the norm of Px equals 1. Sometimes we just say find the norm of 1. And so that's going to be the integral from -1 to 1 of the product of 1 times 1. So that's just going to be x evaluated from -1 to 1. So that'll be a 2, because 1 minus -1 is 1 plus 1 is 2. So the norm here, that was the norm squared. So the norm is going to be the root of that. So the norm of this polynomial, the one polynomial, is root 2. Now we want to find the inner product of the polynomial 1 and the polynomial x here. Part B, we're going to work this, and then we're going to check to see if they're orthogonal. So the inner product is going to be the integral from -1 to 1 of 1 times x dx. So that's just a half x squared using the power rule, evaluated from -1 to 1. And so that's just a half times 0, because 1 minus 1 gives us a 0 there. We get that because we're squaring, right? So the 1 squared and the -1 squared by symmetry, they're both positive ones. So this is just 0, so these are orthogonal. And you could think about that, because imagine the polynomial 1 and the polynomial x, which is just the line through x. So important note, you might be thinking, if you draw out the horizontal line P of x equals 1 and the line x in R2, they're not orthogonal in R2. So it's important to remember here that we're not thinking about these polynomials in R2. We're thinking about them in polynomial space, and we're defining the inner product following this definition, the integral from -1 to 1. So on that interval, -1 to 1, P of x times Q of x integrated with respect to x. So in Rn, or in R2, 2 dimensions, if we graph these out, they're not going to be orthogonal. But in terms of the definition of polynomial space, because we're not in the real numbers now, we're in polynomial space, and this inner product, anything with inner product 0 here, following this definition, is considered polynomially orthogonal. So this set of polynomials, of which these are the first two, are known as the Legendre polynomials. And they're the polynomials in polynomial space that are orthogonal to each other following this definition of inner product space. So you can kind of let your brain think about that. We're not going to go too far in depth into polynomial space in this class beyond looking at examples and applications. So you can kind of let that sink in, that if we're not in R2, our usual definition of orthogonal is a different definition based on the inner product space we're in. Okay, so now still in our polynomial space with that same polynomial inner product, we're going to find the angle between 1 and x squared and figure out, are they orthogonal or not? So we're going to do the inner product of 1 and x squared. So that's the integral from -1 to 1 of x squared with respect to x. So that's going to give us 1/3 x cubed evaluated from -1 to 1. So that's going to give us 1/3 times 1 plus 1, or 2/3. So these are not orthogonal. And then we check the norm of x squared because we're trying to figure out the angle. And we know the norm of 1 is √2. So that's going to come into play down here from our previous calculation over here where we found the norm of the 1 polynomial. And so the norm of x squared, we'll do the norm squared first. That's going to be x squared inner product with x squared. That's just going to be the integral from -1 to 1 of x to the 4th. So that's going to be 1/5 x to the 5th evaluated from -1 to 1. And so that's going to be 1/5 times 2, or 2/5. So the norm of x squared is going to be the root of that, √2/5. So that comes into play down here in our angle calculation. And then the inner product is the 2/3, which we have on top here. So our angle is going to be the arc cos of this calculation, 2/3 over √2 multiplied by √2/5. So we can do some simplification and rationalization there to get that this is going to be the arc cos of √5/3. So that works out to be about 0.73 radians, or 41.8 degrees. Okay, so in the next videos, we'll take a look at Theorem 5.8, which is about vectors in the inner product space V, and continue with some more examples.